Hey everyone, this is Dr. Walker. In this video, we're going to do an example from v519, potential energy of point charges. In this example, we have a positive charge of magnitude 4 microcoulombs is placed at each of two corners of an equilateral triangle of side 2 centimeters. So I have drawn that for us. We have the two charges Q here, these positive charges, and the distance I just wrote it as A. How much work must be done to bring a third positive charge of equal magnitude from far away, or infinity, all the way to that third corner of the triangle? So, first of all, really pay attention to what the question is asking. It just wants to work to bring the third charge, not the work to assemble all three charges together. If we had just wanted to assemble all three charges together, then the work to assemble all three of them would just be equal to the potential energy of the system of charges, which would be Ke, and then you'd have, we got this Q here, right? We'd have Q1, Q2 over A plus Q2, Q3. It's always over A plus Q1, Q3 over A. So we can see that we would get 3 times Ke Q squared over A as the energy. But that's not what it's asking. It's only asking for the work to bring that third charge. So let's look at it differently and think about, well, how much work is it to bring in just a first charge? Right? To bring in just a first charge, it doesn't take any work, because when you're only bringing in one charge here and there's no other charges here, you're not working against any force, right? You can just put it there. That doesn't require any work. What about the work to bring in the second charge? Well, that work is going to be equal to the potential energy of the system. So the second charge here, this is the second charge, this is the first charge. When this third charge isn't here yet, when you're bringing the second charge, that work is equal to the potential energy of those two charges. So that is just Ke Q squared over A. What about the work to bring in the third charge when the other two are already there? Well, you can think about the fact that you're doing work against the force from the first charge, and you're doing work against the force from the second charge. Or another way to think about it, you're going to do work that's equal to the potential energy of these two and work that's equal to the potential energy of these two. So you're going to have 2 Ke Q squared over A. So that's actually our answer over here, and you can see that if you add up the work to bring in all three charges, you do get the 3 Ke Q squared over A. But for our case, just to bring in the third charge, we're going to have 2 Ke Q squared over A. So 2 times 8.99 times 10 to the 9 for coulombs constant times 4 times 10 to the negative 6 coulombs squared for the charge. And the A is a 2 centimeters or 0.02 meters. Plug all this in the calculator and we'll get 14.4 joules. So that's it for this example. Hopefully you can relate the work done to bring charges together to the electric potential energy of that system of charges.